Alright, you all ready?
Yes.
Hello, my name is Eric, and as you can see, my presentation is on the use of heterogeneous catalyst in landfill leachate treatments. Now, you might be asking, what is landfill leachate? It's, as you can see in the picture, that disgusting liquid. Landfills are places where we store waste. They're not necessarily the cleanest of places, and one of the major problems is that when it rains, you normally don't have a roof over your landfill, water will percolate through the landfill, stripping out soluble organics and other nasty chemicals, and acts as pretty much a wastewater. Now the question is, why do we need to treat landfill leachate? As I mentioned before, leachate will generally contain organic chemicals, alcohols, like not the nice alcohols we like, but the ones that kill us. It will contain inorganic chemicals, the common cations and anions, heavy metals, mercury, arsenic, lead, and xenobiotic organic chemicals. Xenobiotics are just a fancy way of saying man-made chemicals. The problem is these chemicals are generally carcinogenic, mutagenic, and we generally don't want to be drinking it. The problem is that this leachate can easily enter the groundwater after soaking through the ground. And, well, we kind of need the groundwater. That's where we get drinking water from. And we don't want to be drinking this stuff. It can cause an environmental and health hazard if it enters the groundwater. So, the problem is landfills are all different. That means that in one landfill, like you have a landfill in America, it's going to be different from a landfill in India, it's going to be different from a landfill in China. There's going to be different stuff in it, different chemicals and whatnot. So you need a method to treat it that can get all of these different types of chemicals that you're going to see. A major problem also is that landfill leachates are generally known for having low biodegradability. Biodegradability is the ratio of the chemical oxygen demand over the biochemical oxygen demand. So it's just the COD divided by the VOD. Just so you know, the chemical oxygen demand, which we're going to be discussing a lot today, is how much oxygen is needed to fully oxidize the organic chemicals in the leachate, while the biochemical oxygen demand is how much oxygen is needed for an aerobic organism, a bacteria, to oxidize that for fuel. The Fenton process is one method of oxidizing a vast variety of different types of organic chemicals. It uses an iron-based catalyst, which is oxidized by hydrogen peroxide, in order to ultimately create a bunch of free radicals that can attack a variety of different organic compounds and break them down. And one of the best things about the Fenton process is that it breaks down these organic compounds into stuff like water and carbon dioxide, which is safer for human consumption. Here's kind of the reaction pathway. We start off with an ion, Fe2+, and as you can see, a reaction with hydrogen peroxide turns it into an Fe3+ and a radical. And then we regenerate the Fe3+ back to an Fe2+ using more hydrogen peroxide and producing another radical. As you can see here, for the contaminant oxidation, the substrate plus the OH will generally give us products such as CO2, H2O, and H3, SO4, 2-. So stuff that isn't as carcinogenic and deadly. One thing that this slide does not mention is how does the Fenton process remove heavy metals? Well, we get, there's an not organic, but a reaction pathway. There's different pathways, obviously, so it's kind of hard to mention them all. The one with arsenic is that you go from a soluble ion into a insoluble precipitate by the oxidation of it. It gets into a different ionic structure, and then it combines with a bunch of irons to make an iron arsenic compound that precipitates out. Now, a couple of drawbacks to the Fenton process, as I mentioned, it precipitates stuff out. So that produces a sludge, which must also be treated. Another issue is with how much iron are we going to use, especially in the homogeneous reaction for it. If we use too little, then we're obviously not oxidizing the leachate as much as we can, so we're not treating it effectively. There's still going to be deadly chemicals in it. But we only have a legal concentration at which we can have iron coming out of our leachate. So that means we can't put in too little, but we also aren't allowed to put in enough or too much. So that's one of the drawbacks of the homogeneous Fenton process. And also, the Fenton process requires an acidic leachate. You need an acid to lower the pH to have a favorable oxidation. Now, we want a heterogeneous catalyst for this Fenton process. And we have a couple things that we're looking for an ideal catalyst. Obviously, we want it to be able to produce the radicals that oxidize the organic chemicals. I mean, if it doesn't produce the radicals, then it's kind of not useful. We want it to be environmentally friendly because we're trying to save the environment, so if we hurt the environment to save the environment, we're going nowhere. We need it to be cheap and widely available. We also need it to be fully or at least partially reusable. This is important, especially in areas that are not as affluent as ours, where the groundwater is their only source of clean water. So if they can't afford to get these catalysts in order to treat the leachate, they're not going to be able to treat the leachate and it's going to enter the groundwater. Bad things can happen. We want the catalyst to be able to be separated from the leachate, obviously. We don't want to have to go through a separation process, which is costly. And we also want to boost the biodegradability of the leachate by lowering its COD. And we want to also do this without killing the bacteria, which would lower the BOD, the biochemical oxygen demand. Now, I researched 4 different types of catalysts for the Fenton heterogeneous process. We have ceria-based catalysts, we have iron-loaded mangosteen shell powder, which is abbreviated MSP, and we have rice husk mesoporous activated carbon, abbreviated MAC. We also have titanium dioxide compounds. Just so you know, all of these compounds are generally support for the catalytic iron. Iron is generally what is used to create these radicals from hydrogen peroxide. Now, the ceria-based catalysts, like I said, they use hydrogen peroxide and iron to create the free radicals. And in this experiment that they had performed, they came up with 4 different types of ceria-based catalysts. The first type is just a basic ceria oxide, labeled CZ100. And this was produced in order to see whether ceria itself had any catalytic effects without the iron and the oxidation process. Then we have ceria zirconium oxide compound. This was done because zirconium has a special type of ability where it can help mobilize oxygen, and they wanted to see how does that affect ceria's ability to act as an active site. Then we have ceria iron compound. This was done to see how does ceria iron interact on a kind of a chemical level, acting as a catalyst. And then we have the main baby of them all, the ceria zirconium iron oxide compound, which is just to see, hey, if we get all these interactions going together, is this going to be a better catalyst? Results not too great. Before I continue on, I need to point out I made a mistake on the slide. Instead of saying 50% removal of COD, it should say 50% removal of TOC. TOC, you can see here, what it stands for is the total organic carbon, which is a different way of, a different test to figure out how much organic compounds are in there. So generally we're going to be using this COD rather than the TOC. Anyway, as you can see here, the yields are not that great, or the abatement or removal of COD is not that good for the ceria-based catalyst. At most, we see about maybe 7 or 8% removal of COD. However, one of the problems with this experiment is that it was just to see, hey, does the catalyst actually work? They weren't necessarily trying to optimize it. We know this because, as I mentioned earlier, the Fenton process requires a low pH for the oxidation to run smoothly. And if you can see here, it's kind of small, but they say that the pH is 9. So it's a fairly basic pH. In the experiment, they weren't necessarily trying to optimize it. They were just testing to see, does it work? However, we do see that there is at least some steady, reliable decrease in COD. And it does remove the total organic carbon, which is a way of saying, hey, if this carbon is, or if this are these compounds organic, or are they non-oxidizable, or are they oxidizable? Now we go into iron-loaded MSP. MSP stands for mangosteen shell powder. And just so you know, this is a mangosteen fruit. It kind of weirded me out. I wasn't used to saying all of these. Anyway, so the mangosteen shell powder is recycled and processed to produce support for the catalytic iron. In this case, what they did especially was they added iron nitrate to a ground up mangosteen shell powder. They then, let's see, I believe they then sonicated it or stirred it, and then they washed it and dried it in order to produce the powder. One of the good things about this support especially is that it allows for easy separation from the leachate for catalytic regeneration. Some of the other catalysts aren't necessarily as easily separable. This one apparently is very separable. Now, it says that MSP is cheaply sourced and environmentally friendly. The environmentally friendly part is true. The cheaply sourced in America is not necessarily so. I looked it up on Amazon. One of these fruits costs about $7, so it's not necessarily economically viable here. But in India, where the experiment was performed, apparently these are a lot more easily found, and it's apparently an easy way to source these for catalytic support. As you can see here, this graph shows the total CV, or carbon oxygen demand, versus the total, so it's kind of showing you how much does it get reduced by. As you see, hydrogen peroxide by itself fairly reduces it a good amount, almost 50%. And that MSP, when you add it without any of the iron, this is just regular shell powder, it also by itself gives you a tiny little bit of increase in the carbon oxygen demand removal. However, when you load it with iron and you sonicate it or stir it, you see a much greater decrease in the total COD. In fact, with the iron-loaded sonicated one, which is the more expensive process to sonicate rather than just stir it, you do get up to 81% reduction in COD. Now, one of the things I have to mention is that this right here, where the MSP removes some of the carbon oxygen demand, that's by kind of acting like a sponge, like kind of sponging up some of the carbon organic compounds. And this might not necessarily be a good thing, because it might allow for easy poisoning of the catalytic iron, because it kind of just absorbs some of the stuff rather than actually getting oxidized. It could poison the catalytic iron. Our next catalyst is rice husk MAC, mesoporous activated carbon. These are rice husks. Rice is pretty much everywhere. It's one of the major staples, so obviously if we have these husks, we can do something to use it. In the experiment that was performed here, what they did was they produced 3 types of catalysts using this rice husk. They would activate it with phosphoric acid, and then they would also, in the activation process, heat it at various temperatures, 700, 800, 900 degrees Celsius. Just so you know, they only ended up using one of them, the 800 degrees Celsius, because they believed it had the most optimum pore diameter, surface area. It was the optimum catalyst for from the experiment. One of the good things about the activated carbon is it helps prevent radical scattering by chloride ions. You need radicals to actually do the oxidation to break down these compounds, and if chloride ions can attack the radicals before they can do anything, it kind of renders the radicals useless. It wastes money, wastes hydrogen peroxide. So the mesoporous activated carbon kind of prevents that by getting the hydroxyl radicals in place to safely attack the organic compounds. And also, just so you know, one of the major issues with this experiment in general, though, is that it uses the homogeneous Fenton reagent, an aqueous solution of iron sulfate. So it's not necessarily a true homogeneous reaction, although it does have some heterogeneous capabilities. This right here is an absorbance spectra. Just so you know, this particular experiment, since like I said, leachate is different from one place to another. This was done, I believe, in Spain. They were using water from a tannery, leather production. So what they were concerned about especially were animal proteins in this experiment. So they were saying that one of the peaks here at 250 and around 280 here would correspond to aromatic amino acids that came from the animal protein. So they want to obviously remove that. So as you can see, the homogeneous Fenton gave some slight decrease in the absorbance spectrum of this, but the heterogeneous Fenton gave you a completely different, completely clear version of this absorbance spectrum. Even knowing how absorbance spectra work, you can see that this means that the water has cleared up considerably. In the literature that I was reading, they said that they start out with 2,100 milligrams of COD per liter, and they ended up after treatment with 580 milligrams per liter of COD, so a 72% reduction. However, since I said as they use the homogeneous Fenton reagent, it doesn't necessarily solve the problems we had earlier of iron being in the exiting stream. So that still becomes an issue when we're using this process.
You still have ammonia in the water, right?
Oh, it's going to have ammonia, definitely. I mean, it's going to require treatment afterwards, but rather than having a dioxin or something that kills you dead, ammonia is kind of like not as big of an issue in comparison.
So you use that water for what? For irrigation?
I believe what they wanted to use the water for was, I believe they wanted to not necessarily make it potable or anything, but they wanted to treat it for, I think, irrigation and stuff like that. They wanted, it's just a pre-treatment before you clean out the water. It's just one section of the landfill treatment facility. Now the titanium dioxide compounds. We all went to Dr. Faraji's lab. We know that titanium dioxide and UV light can clear up wastewater. In this case, we have the photo-Fenton and also ozone-based reaction. So titanium dioxide can do two different types of catalytic reaction in order to clear landfill leachate. Generally speaking, it requires iron in the Fenton process for landfill leachate treatment. And when it's used alone, the literature said that it had somewhat of only a minimal decrease in COD.
Does it give UV?
It required UV in the experiment. They had a UV.
They have UV?
Yeah, they had UV.
In the presence of iron? Or no?
Yes, in presence of iron.
Oh.
This is the graph that kind of shows the homogeneous Fenton reagent, once again, FeSO4, and also the heterogeneous catalyst, WTiO2. The W does not stand for tungsten. What they did in the project, or in the report that I read, the W just meant that it came from certain waste that was produced from, let's see, that this was produced as the waste of the sulfuric acid digestion of ilmenite in order to produce titanium metal. This was just a waste, and the W just means it's doped with iron. So it's an iron compound, iron titanium dioxide compound. So on this left-hand graph, we're mostly concerned with this blue line, which indicates COD. So you can see here, you start off on both ends with around 6,000 milligrams of COD per liter. And on both ends, they kind of end up at the same place, about roughly 500 milligrams of COD per liter. But what's interesting is this x-axis right here, where we see that it corresponds to hydrogen peroxide consumed. The homogeneous reaction, or homogeneous catalyst, required 13 milligrams, or 13 grams of hydrogen peroxide in order to oxidize it to the same area, when the heterogeneous only required 5 grams per liter of hydrogen peroxide. So it's more efficient with hydrogen peroxide. You buy less of hydrogen peroxide to save more money. Now we also can use it, we can also use ozone as an oxidizer, because the Fenton reagent isn't the only thing that can do oxidation, right? A lot of literature supports ozone as an oxidizer, although some literature says it's not hugely successful by itself. However, one of the good things about ozone is you don't need to lower the pH. The other ones, you did need to lower the pH. So that could save you some money in terms of pretreatment. We have 3 different types of catalysts for the ozone-based oxidation. We already spoke about 2 of them. Titanium dioxide is good. Activated carbon, we also talked about, that's been useful. One of the more interesting ones that I read, though, was perlite. Perlite is a volcanic glass. It's non-renewable. However, it has a high surface area, it's safe, it's lightweight. And let me tell you, it is cheap. I checked on Google for 1 metric ton, 1,000 kilograms, $49. So it's very, very expensive. And it's also somewhat efficient. As we can see here on this graph, this is COD removal, y-axis. And ozone by itself gives you around 20-ish percent removal of COD by itself. And as we can see here, the other catalysts gave you up to 40% removal of COD. Not as good as some of the other catalysts we discussed, which had 70%, 80% removal, but still not bad, seeing as we don't have to use acid to pretreat it. In the end, it seems like activated carbon wins out, and titanium dioxide is kind of a middle, whereas perlite, although it's fairly cheap, kind of doesn't do anything here. But if you take a look here, I mean, it almost maxes out right around the 1 gram per liter of, or 1 gram of catalyst per liter of leachate mark. So it might be fairly efficient if you just had somewhat lower concentrations. So obviously the question is, what is the best catalyst? And unfortunately, it's not necessarily in the scope of this presentation to determine which is 100% the best. Stereo-based catalysts, for example, as we mentioned, they weren't necessarily optimized. It was more of an experimental catalyst to see if it could work. So if they managed to optimize it, the yield or the removal of COD could be a lot better. We also have iron-loaded MSP and rice husk MAC. And they're both safe and fairly cheap, but MSP, as I mentioned, could be easily poisoned because it acts as a sponge. And the MAC requires the homogeneous Fenton reagent, which doesn't necessarily solve our problems as mentioned earlier. The photofenton process using iron doped with titanium dioxide might not necessarily be viable with places with a lot of rain, not a lot of sunshine. You know, really up north, really down south, you might not be able to use it very effectively. And ozone-based oxidation doesn't have as much removal of COD as the others do. However, it can operate without necessarily lowering the leachate's pH. So it could be useful if you don't want to spend money on acid. Any questions?